Does the universe have a right side up? In a nutshell, no it doesn't. Some of what I'm about to say is so obvious, but bear with me. Whenever we look at something, or take a photo, make a film, or draw a diagram, we assume that up is pointing towards the ceiling or the sky, if you're outside, and that down is pointing towards the floor, and ultimately the centre of the Earth. First of all, the Earth is a large, spherical object to which we are attached by gravity. It takes a huge amount of effort and energy to get ourselves away from it. This gravity always pulls us towards the centre of the planet, and if it weren't for the ground, the surface, and the fact that the Earth is made of solid matter, we would fall all the way to the centre of gravity. So up for someone in Spain is pointing almost exactly in the opposite direction to someone in New Zealand. And as the Earth spins on its axis once every 24 hours, so does up from our moving frame of reference. Second of all, the Earth is orbiting the Sun, a huge object, 93 million miles away, taking 1 year to travel all the way round. Thirdly, the Sun itself, a very average star, takes about 220 million years to orbit the centre of the galaxy, which itself is composed of about 200 billion other stars. And fourthly, our galaxy is one of billions in the known universe, most of which is expanding, not from a central point, but clusters and superclusters of galaxies are all moving away from each other. It just so happens that what we call north is usually up on maps and globes, but humans could just as easily have chosen south as up. Maps would still make sense, but apart from a few upside-down road maps, it keeps things simple by having north at the top of the page. As far as the Big Dipper is concerned, saying that it only looks like it does from this planet is something of an understatement. The Big Dipper would look the same to us from anywhere in our solar system, from the Sun to Neptune and beyond, into the realm of the comets, the Kuiper Belt. Interstellar distances are so vast that to say our closest neighbouring star, Alpha Centauri, is just over 4 light years away means that it takes 4.2 years for its light to reach us. Light travels at 186,000 miles per second, which means Alpha Centauri is about 24 trillion miles from us. And that is the closest star. Most of the brightest stars we see in the night sky, including all those in the Big Dipper, are within a few hundred light years. Our galaxy is 100,000 light years across, and we are about 26,000 light years from the centre. So if we could travel to other local stars, which we can't with present technology, the patterns of the constellations would be different, because the individual stars we see in the recognisable patterns are at different distances from us. There is no right side up because there is no fixed point of reference. Everything in the universe is moving relative to everything else, and as far as we can tell, the universe is similar in all directions. The closest approximation we could imagine would be a 3-dimensional grid expanding with the universe, but it is easiest to abandon the concept of a fixed position and accept that everything is relative and on a local level focus our attention on the Earth. In these videos, I'm going to try to describe how I learned about astronomy. I have no formal training and I'm not a teacher, but I do have a passion for the subject. This will not be a comprehensive or even conventional video series. What I mean by that is that I will be covering some very basic concepts as well as some more advanced subject matter. There are many other videos on YouTube which go into great technical detail and complex mathematics. I will try to keep things reasonably simple and connect them to things everyone can relate to, wherever possible. When I was a kid, I lived in a big city where the light pollution meant that on a clear night you couldn't see that many stars. Sometimes we went on a family holiday and stayed in a cottage in the country, far from city lights. On a handful of occasions, I was amazed by the beauty of the night sky and got a sore neck from looking up for so long. Through my binoculars, especially if I steadied them against a tree trunk, I could see so many more stars between the ones I could see without binoculars. I wondered how far away they were, whether they moved over time, which ones were planets, and so began my interest in astronomy. The closest astronomical object to us is the Moon. It is very familiar to us, but how much do we actually know about it? It's a huge ball of rock which orbits the Earth at over 2,000 miles an hour once every 27 and a bit days. It is held in a stable orbit by its motion and gravity. I'll come back to gravity and orbits in a future video. Everyone is familiar with the phases of the Moon. As it orbits the Earth, a different part is illuminated by the Sun. From the Sun's point of view, the Moon is always full, but from our point of view, the phases of the Moon repeat every 29.5 days. This is different from the 27 and a bit day orbit because the Earth-Moon system is itself orbiting the Sun. The speed of our orbit around the Sun is much faster than the Moon's orbit around the Earth. So if you were observing from Mars or somewhere far away, you'd see the Earth-Moon system whizzing around the Sun at about 66,000 miles an hour, which is about 25 times faster than the speed of the Moon orbiting the Earth. How far away is the Moon? To get an idea of the relative scale, the distance is approximately 30 Earth diameters or 110 Moon diameters. The distance is about 238,000 miles, nearly 250,000. The average car will probably drive less than half that distance from the showroom to the scrapyard. Between 1968 and 1972, 9 NASA Apollo missions went to the Moon and back, and it took them about 3 days to go each way. In 3 days, the Earth-Moon system travels about 5 million miles around the Sun. That's about 20 times the distance from the Earth to the Moon. So although the astronauts were traveling as fast as they could relative to the Earth and Moon, they were traveling much faster relative to the Sun. Try to remember this concept. I'll be coming back to it in a future video when we tackle Einstein's theory of relativity. So now we have an idea of how far away the Moon is and how it is moving. What about the size? How big is it? Well, the diameter is 2,160 miles. Not that different from the size of Australia. It is just over a quarter the diameter of the Earth, or 3/11 to be more accurate. The Moon is ever so slightly pear-shaped, and I mean slightly. It's as round as a billiard ball, but the bulge is enough to keep the same side facing the Earth. The mass of the Moon, or its weight, is about 1/80th that of the Earth. Although I've said that the Moon is orbiting the Earth, it's more accurate to say that the Earth and Moon are orbiting each other around their common center of gravity, the barycenter. Because the Earth has 80 times more mass, the barycenter is within the Earth, but not at the center. The Earth has the largest moon in the solar system, relative to itself. There are larger moons, but they are orbiting the gas giants. But more about them in future videos. There are several theories about how the Moon got there. One of the most plausible is that early in the life of the solar system, probably more than 4 billion years ago, the Earth and another planet collided, and the resulting debris coalesced by gravity and its motion into what became the Moon. It used to be closer to the Earth, and is moving away by just over an inch per year. I can't explain the exact reason for this, but I believe it has to do with the frictional effects of the tides. I mentioned before that the mass of the Moon is 80 times less than the Earth. You might think that the gravity is 80 times weaker, but this is not so. If the moon were the same size as the Earth, but the mass was still 1/80th, then the surface gravity would be 1/80th. But because it is 3/11ths the size of the Earth, the gravity is about 1/6 as strong. The Apollo astronauts, despite their heavy spacesuits, were able to jump higher than they could here on Earth. Personally, I would love to go to the moon one day, to be able to jump 6 times higher, and also to be able to look back at our home planet. In a possible future lunar base, the Earth would always be visible in the same part of the black sky. The stars would not twinkle, as there is no atmosphere to distort their light. The lunar day is a fortnight long, followed by a cold, dark 14-day night. This could take a while for humans to get used to. One thing I would like to see NASA or anyone else do is to set up a lunar observatory. With the lack of atmosphere and slow rotation, I'm sure we could learn a lot more about the universe. However, I'm sure there are good technical reasons why this hasn't been done yet. If anyone has any astronomy-related questions, please let me know, and that may have an influence on my future astronomy videos. Thank you. When we look out into space, it helps to have an understanding of the speed of light. We use it more often to measure astronomical distances than to measure the motion of physical objects. At first it might seem strange to use time and light to measure distance, but it is a very useful way to understand the astronomical vastness of space by calculating how long it takes light to reach us from different objects, such as the moon, planets, the sun, other stars, and galaxies. So how fast is it? Well, the speed is exactly 299,792,458 meters per second, which is just over 186,000 miles per second, or about 670 million miles an hour. Not only is this incredibly fast, but nothing solid, nothing with mass, can be accelerated to this speed. Our fastest spacecraft move at a fraction of 1% of the speed of light. However, we can accelerate subatomic particles to within a very small fraction of 1% of this speed, at places like the Large Hadron Collider at CERN in Switzerland. I plan to come back to this in future videos. Most people are familiar with the term light year. A light year is the distance light travels in 1 year, 5,878,625,373,183.6 miles, or 9.461 times 10 to the 15 meters. This last figure, for those who don't know, is abbreviated and expressed in System International or SI units, which all scientists should be familiar with. To write it out longhand, you need to move the decimal point 15 places to the right. In SI units, distance is always measured in meters, mass in kilograms, and time in seconds, and so on. All physics equations can be reduced to 7 standard units of measurement. This is a good time to mention that the speed of light is referred to as c. So the c in E equals mc squared means that energy equals mass times c, the speed of light, squared. How can we understand c better? One way I think is helpful is with the following thought experiment. Imagine that there is a very large mirror on the moon, angled so it is facing towards us. Now imagine you have a very large telescope pointing at the moon, so you can just make out this extremely large mirror. You happen to have a very bright light which you flash while looking through the telescope. You will see the reflection of the flash 2.6 seconds later. 1.3 seconds for the light to go to the moon, and another 1.3 for the light to come back. The moon is about 238,000 miles away, which is 1.3 times 186,000 miles, which is 1 light second. If you listen to the unedited recordings of the conversations between Neil Armstrong and Houston from the moon landing in 1969, you will notice a significant time delay. Neil seems slow to respond. If the recording had been made on the moon, Houston would have seemed slow to respond. This is because radio signals also travel at sea. They are similar to light, but further along the electromagnetic spectrum. So our eyes can't see radio waves, but our radios can turn them into something our ears can make sense of. So knowing what C is, we can say that the moon is 1.3 light seconds away. The sun is just over 8 light minutes away, 93 million miles, which is about 400 times further than the moon. You will notice that I use a lot of abouts and approximately's. One reason is that orbits are elliptical, close to circular, but not quite. The other reason is that we don't need great accuracy and very long numbers to get an idea of how it all fits together. Neptune, the outermost large planet in the solar system, is 30 times as far as we are from the Sun, which is about 4 light hours. The furthest man-made objects, the Voyager space probes, are currently about 4 times further than Neptune, which is still less than 1 light day. But this distance is tiny in the grand scheme of things. The closest star, other than our Sun, is Proxima Centauri, which is just over 4 light years away. Voyager 1 would take about 76,000 years to get there, if it were heading in that direction. The brightest star in the night sky, Sirius, is about 8 light years from here. It's not a particularly big star, but it happens to be relatively close. All the bright stars we see in the night sky are well within 1,000 light years. Those further away can only be distinguished with telescopes, but to our eyes, most of them are lost in what we call the Milky Way, the plane of our galaxy, as seen from within. We are located about 26,000 light years from the galactic center, in a spiral arm known as the Orion Spur. The whole galaxy is about 100,000 light years across. So if there were a technologically advanced civilization living on a planet orbiting a star more than 100 light years away, they would not be aware of us, because we haven't been broadcasting radio signals for long enough. For this reason, we are only just beginning our search for life and civilizations in other star systems. We've only scratched the surface so far. We're limited by the speed of light and the huge distances involved. The nearest large galaxy, Andromeda, is 2.5 million light years away. The empty space between our own Milky Way galaxy and Andromeda is over 20 galaxy widths. The known universe contains billions of galaxies in all directions. As we look out into space, we are effectively looking back in time. It takes the light from more distant objects longer to reach us. Because the universe appears to be very similar in all directions, we can, by looking outwards and back in time, get an idea of what the universe used to be like. I shall expand on this in future videos. There is a force which attracts all matter in the universe to all other matter in the universe. The fact that the material stuff of the universe is in motion prevents it all from crashing together into one huge lump. We call this force gravity. On a small scale, gravity is very weak. If you were to stand on an asteroid, you could jump very high and float gently back down. It would be hard to hurt yourself by falling. Here on Earth, we experience gravity at a strength of what we call 1g. It is a force which can be expressed as an acceleration of 9.8 meters per second towards the ground. You would probably survive tripping over a row of matchboxes, but a fall from a tall building would almost certainly kill you. We can't tolerate much more than about 5g. This amount of acceleration is not a pleasant experience. The gravity on the surface of the Sun is 28g, so apart from the fact that you'd be instantly fried, the gravity would squash you like a pancake. As I mentioned before, the motion of objects stops them from crashing together. Objects can be in motion, or orbit, around larger objects. Moons and satellites are in orbit around planets, which are themselves orbiting stars. Smaller stars orbit larger stars in binary systems, or, if the sizes are similar, they orbit each other. Or to be more specific, they orbit their common center of gravity, their barycenter. Star systems orbit the center of their galaxies, and galaxies are involved in a complex dance which is far slower than this animation would suggest. The distances and timescale mean that we can look at galaxies from one decade to the next and not see any movement. So how do we know they are moving at all? Well, briefly, it is inferred through the redshift and blueshift of their light. We can tell which part is moving towards and away from us. I shall return to this in future videos. An interesting thing about gravity is that it dictates the shape of large solid objects. All stars, planets and large moons are spherical. In general terms, matter is not strong enough to remain in irregular shapes if it is part of an object more than a few hundred miles across. The largest object in the asteroid belt, between the orbits of Mars and Jupiter, is Ceres. It is about 600 miles across and could be described as a planetoid. This is what it would look like next to the Earth and our Moon. Smaller asteroids are less spherical. Mars has two tiny moons called Phobos and Deimos, which could well be captured asteroids. Gravity can pull objects from one orbit to another. If an asteroid happens to pass too close to a planet, it can crash into that planet or end up orbiting it. The maths involved is too complex for me to explain, but it is possible to understand the basic principles without too much maths. Something which is relatively easy to understand is the inverse square law, which describes the strength of gravity at different distances from a star, planet or moon. Here is a thought experiment. Imagine a moon which looks like a giant golf ball. At every dimple there is a laser pointing straight up. If you are close to the moon, you will have many laser dots on you. If you are further away, you will have fewer dots on you. The more dots, the stronger the gravity. Due to the stronger gravity closer to a star or planet, a planet, moon or satellite must travel faster to remain in a stable orbit. It takes the Earth 1 year to orbit the Sun at a speed of 66,625 miles per hour. Saturn is nearly 10 times further from the Sun and takes 29.46 years to orbit at a speed of 21,576 miles an hour. Albert Einstein published his General Theory of Relativity in 1916. It still contains the best description of gravity we have. Galileo, Newton, Kepler and others were among the first humans to calculate the strength of gravity and the maths behind elliptical orbits. We still use Newtonian physics, even though Einstein refined and improved upon it. That's because Newton's laws of motion are very close to what we observe, especially on a local scale. A brief summary of the relevant parts of general relativity is that gravity and acceleration are indistinguishable. If you're in a lift, or elevator for my American friends, which was in free fall, you would experience the weightlessness of space, until you hit the bottom of the lift shaft, that is. Now if you have the same elevator in a rocket in space, with the floor facing the engines, and you accelerated the rocket at a constant 1g, you wouldn't be able to tell that you weren't in a building on Earth waiting for the doors to open. The important thing is that you can't feel whether you're in constant motion or not, whether there is a force acting on you or not. So gravity and acceleration are basically the same thing. A straight line and a curved line are hard to tell apart on a local level. The edge of your house might be a straight line, but if you extend that line along the ground far enough, it will form a giant circle. But you'll only know it's a circle if you can see the whole planet. According to general relativity, objects move in straight lines through space and time, unless something like gravity affects them, and we can then conclude that space-time is in fact curved by objects with mass. Gravity is the curvature of space-time. This is another subject I plan to return to in future videos. Despite what we do know, gravity is the least well understood of the four physical forces. The mechanism of the attraction of matter at a quantum or subatomic level still holds mysteries. You might be wondering why there is so much physics in an astronomy video. In order to understand what's going on in the world of astronomy, you need to know some physics. There is a lot of overlap between the two subjects. It's often referred to as astrophysics. The successful unification of general relativity and quantum mechanics still eludes physicists. I find it funny that in 2011, millions of people still take horoscopes seriously. As a species, we have been to the moon, explored the solar system, and discovered an amazing amount about the universe. Yet some of us believe that planets millions of miles away and stars trillions of miles away affect our personality and daily lives. In order to understand astrology, we need to understand a few basic astronomical concepts. Once you get your head around some of the astronomy, you will see how a lot of the astrology, particularly horoscopes, is riddled with nonsense. You should all be familiar with the 12 star signs of the zodiac, but what does it mean to say that someone is a Capricorn? Well, if you were born on the 25th of December 2000 years ago, the sun would have been in the constellation of Capricorn. This means that if the sun wasn't in the way, you'd see Capricorn. It takes the Earth 1 year to orbit the sun, and we always go in the same direction and on the same plane, which means that the sun is always in front of one out of the 12 zodiacal constellations, man-made patterns in the distant stars. There are 88 constellations or groupings of stars in the night sky, 12 of which are in a band known as the ecliptic. They only look the way they do from our solar system. If we were to travel to other star systems, the patterns would be different, more so the further away we went. So the idea that the constellations have an actual effect on us is absurd. It is better to think of them as markers, similar to the numbers on a clock, merely an indication of the sun's apparent location. The star signs, as those who are familiar with horoscopes will know, change at about the 20th of each month. The 21st of March is an important date because it is the vernal or spring equinox, the point where day and night are of equal length and the northern hemisphere is approaching its summer. In the past, the year began at the spring equinox. The month September used to be the 7th month of the year, October the 8th, November the 9th. The Earth is tilted at 23.5 degrees to the plane of its orbit. The polar axis is always pointing at the same point in the sky, at least on the scale of a human lifetime. The North Pole points to the star Polaris, and the South Pole points close to the Southern Cross. Because of this 23.5 degree tilt, we have noticeable seasons, which makes it easy to tell one year from the next. Now we come to where modern astrologers are wrong. The vernal equinox changes over time because the Earth's axis wobbles or precesses and describes a large circle which takes about 25,920 years to describe a complete circle. So the vernal or spring equinox precesses or moves backwards through the signs of the zodiac in what is referred to as an astrological age. Each age lasts for about 2,160 years, which interestingly and coincidentally is the moon's diameter in miles. So we are at the end of the age of Pisces and coming into the age of Aquarius. The astrological age depends only on the apparent position of the sun at every spring equinox. But if you look up your horoscope, you will see that it hasn't been updated for over 2,000 years. So your actual birth sign and your horoscope sign are askew by one sign. I'm a Pisces, but I should be an Aquarius. Aries are actually Pisces, and so on. The idea that the position of the planets makes any difference at all is rather tenuous. The gravitational effect is almost vanishingly small. Even Jupiter, the most massive planet by far, is so far away that it takes light almost an hour to travel that distance, never mind any other effect. The Sun, however, does affect us with radiation and the strong gravity which holds us in a stable orbit. I've heard it said that sunspot cycles and the magnetic fields from the Sun affect us on 11-year and 4-monthly cycles, and that this might explain some astrological claims. I'm not sure whether this is an avenue of pseudoscience or not, but I may come back to this in future videos. So to summarize, I would agree with Carl Sagan that astrology is bunk, particularly in terms of daily horoscopes, but I wouldn't dismiss the possibility that solar radiation has some sort of effect upon us.
How could it possibly work? How could the rising of Mars at the moment of my birth affect me, then or now? I was born in a closed room. Light from Mars couldn't get in. The only influence of Mars which could affect me was its gravity. But the gravitational influence of the obstetrician was much larger than the gravitational influence of Mars.